speaker is myself. Let me go full screen. Okay. So I will talk about first order quantum phase transitions in the context of quantum field theory. This is work.
Sorry, Nikos, maybe you should maximize your screen, I think.
The screen, you can't see the screen? I am full screen.
Sorry, my fault. Yes, you're right. Sorry.
Okay. Okay, so this is based on work with my student Fotis Koutroulis, which was published in a recent paper, and also many other papers, several other papers that are referenced in this paper. So even though this is going to be a very basic, straightforward quantum field theory, since this conference is about holography and discrete approach, I will try to make some comments about a possible connection to holography, and there will be also some discrete approach involved. Now, first order quantum phase transitions. First of all, let me just explain a little bit what this is. Quantum phase transition is a phase transition that occurs at 0 temperature. And first order is a phase transition which is not as a second order phase transition, which is supposed to be a phase transitions where there is a continuum limit. A first order phase transition is a phase transition where there is no continuum limit. So this is just very generally what is the context. Now, and I will be interested in describing what happens in the vicinity of such a phase transition. Now, in a quantum field theory, since I will be discussing systems which are not in the, let's say, condensed matter world, but in the high energy theory or particle physics world, I will be talking about mostly quantum field theories in 4 dimensions or higher. And I will think of these quantum field theories as defined by the use of a regulating scale, which we can think of as the scale mu that one introduces when regularizes quantum field theory by dimensional regularization. So in this scheme, in this regulating scheme, quantities depend on the scale mu, and this dependence can move us around the phase diagram of such a system, and in particular, we can use it to move towards or away from a phase transition. So these are what we call the RG flows. Now let me first review a little bit second order phase transitions, which are more perhaps more familiar, or if not more familiar, they are easier to usually to analyze in a quantum field theory context. And the most familiar second order phase transition is basically a Gaussian fixed point. Now, at a Gaussian fixed point, usually one does not say that there is a phase transition. However, if we extend a little bit the notion, we can think of the Gaussian fixed point as a second order phase transition by defining the 2 sides of the phase transition, except that in this case, there are not just 2 sides, there are an enormously large number of sides, just because of universality. So many systems, millions of systems can land at the same Gaussian fixed point, and then one can extend the notion and say that the Gaussian fixed point, there is a phase transition, and on one side you have an Ising model, for example, like I show you in this picture, and on the other side I may have a scalar QFT. What is important to remember is that at this point there is a continuum limit. Continuum limit means, in the language of the regulating scale, that one can take the regulating scale to infinity. So, of course, in particular, quite often, this is a point where the symmetry of the system gets enhanced. So it becomes a conformal field theory, for example, etc., etc. In quantum field theory, usually we're not sitting on the Gaussian fixed point, even though we could describe the Gaussian fixed point by CFT techniques. But usually what we learn in a quantum field theory course is what to do on the scalar, let's say QFT side, in the vicinity of this phase transition. Okay, applying, for example, perturbation theory. And then we know that in the vicinity of this phase, of this Gaussian fixed point, we can go closer and closer to the point, and the regulating scale, the cutoff of the theory, becomes larger and larger and larger and larger until it lands on the fixed point, and at that point, the cutoff becomes infinite. So first order now phase transitions are a bit more complicated. First of all, they are much harder to probe in the continuum. Let me give you an example. So let's take a very simple quantum field theory, a scalar theory with a mass m squared phi squared and an interaction term lambda phi to the 4 in 3 dimensions. Just an example. And this is the phase diagram of this system. Now, this blob at the origin, so you see here that there are 2 axes. The vertical axis is the mass squared as a function of the regulating scale mu. On the horizontal axis, I have the self-coupling as a function of mu. The origin is the Gaussian fixed point, is the point where the system does not have a mass, does not have interaction, it has only a kinetic term, and this is called the Gaussian fixed point. And perturbation theory usually takes place near this Gaussian fixed point. However, if you extend a little bit perturbation theory, namely, if you set the epsilon parameter of dimensional regularization, and the epsilon parameter is defined as 4 minus d, for example, where d is the dimensionality, you can set epsilon equal to 1, and is not an infinitesimal parameter, but you can set it equal to 1. And if you do that, you discover another point where the beta function vanishes. Let's say the one loop beta function vanishes. And then one says that, oh, okay, this may be a sign of a second fixed point, which is called the Wilson-Fisher fixed point. Now, usually, the vanishing of the one loop beta function is interpreted as a fixed point. I'm going to take a slightly different point of view here and say that it may be the sign of a second order phase transition or a fixed point, but it may be a sign of a weak first order phase transition. This means that maybe the one loop beta function vanishes, but that doesn't mean that the 2-loop beta function will vanish or the 3-loop beta function vanishes. It's just saying that the system is trying to become a second order, to have a continuum limit at this internal point, but it may or may not reach the continuum limit. Okay, if this is the situation, so let's say the 1-loop beta function is 0, the 2-loop beta function is 0, but then the 3-loop, 4-loop, 5-loop beta functions are non-zero. So that would not be a fixed point, but it would be most likely the signal of another type of a phase transition, which is a first order phase transition. Okay, but nevertheless, the fact that the beta function vanishes to a certain loop order is an indication, it's a sign of a phase transition somewhere in the interior of the phase diagram. Okay, so now in perturbation theory, or even in the epsilon expansion, which is a modest generalization of perturbation theory, we are not really sure that such a point really exists, but it's very interesting because then we can connect these 2 points via renormalization group flows, and we can ask the questions: what happens in the vicinity of this phase transition, not the Gaussian, but this phase transition. Except that now to do actual calculations in the vicinity of this second phase transition here is not so easy, because for many reasons, one of the reasons being that the epsilon parameter of dimensional regularization is supposed to be infinitesimal. Nevertheless, you set it equal to a finite value, equal to 1 or -1. If you set it to -1, you can go to 5 dimension. If you set it to -2, you go to 6 dimension, etc., etc. And this is not something that is guaranteed to work. So, but what I will keep for the following discussion is that you can see that the arrows here on the RG flow lines point toward the infrared. Okay, so you can see that if this phase transition, for example, if this Gaussian fixed point, for example, is an ultraviolet fixed point, then this star point here will be an infrared fixed point. In 5 dimensions, the situation would be reversed. One would be infrared, the Gaussian would be infrared, the star, the Wilson-Fisher, would be ultraviolet fixed point. Okay. So one of the reasons that we are interested in this setup, in this quantum, first order quantum phase transition, is that they give rise to non-trivial effective field theories with a finite cutoff. Okay, and this is the real world. Okay, so this is the, if you wish, the standard model. So a natural question that one can ask: how can you describe the vicinity of a first order phase transition with a finite cutoff? And of course, one can then also assume a picture where the standard model itself, sometime, somewhere, set near a first order phase transition, and maybe still sitting near a first order phase transition, or maybe it had moved away from it, etc., etc. Now, when the phase transition is an ultraviolet phase transition, we are familiar with a classification of operators as relevant, marginal, and irrelevant. And when near a Gaussian fixed point, this is the usual classification. And this is very useful because then the mass is a relevant operator, the lambda phi to the 4, let's say, interaction is a marginal operator. And then if you start adding higher dimensional operator, they are classified as irrelevant, basically because when you take the continuum limit, which we know we can take near a Gaussian fixed point, they just are washed out. They give some corrections, but they are irrelevant. Now, when the phase transition is first order, sometimes this can be a very confusing classification. For example, take the mass parameter in a theory to 0 and consider systems that then become classically scale invariant. Then we let the system develop its own interaction, and then we discover that neglecting the irrelevant operators is an allowed operation for the Gaussian fixed point, but not necessarily so for the first order phase transition. Why? Because if there are no relevant and marginal operators, then all the physics, all the non-trivial physics, is generated by the higher dimensional operator that you would classify as irrelevant. So they cannot be as irrelevant as in the vicinity of the Gaussian fixed point. And I will give, of course, I will give a specific construction that has precisely this property. And another way to put this is that the only classical limit of the system is the continuum limit that forces the system towards the Gaussian fixed point. If there is another phase transition, which is in the interior of the phase diagram, in that in that phase transition, there is no classical limit. So, and this can be very nicely illuminated in a system that does not allow polynomial interactions at all. Then the physics in the vicinity of the phase transition is determined by relevant operators. Okay, so let's now look at a specific example, which is nothing else other than SUN pure Yang-Mills theories in dimensions 5 or higher. In fact, all these theories, all pure SUN Yang-Mills theories in dimension D 5 or higher, they possess such a first order phase transition. So this is, I will discuss mostly the simplest case, which is D equal 5 and N equal 2, so SU2 Yang-Mills in 5 dimensions, but many of the things that I will say hold for any SUN in any dimension as long as the dimensionality is not infinite. So the phase diagram of this system has two phases. Okay, so since there is a phase transition, it means that the phase diagram breaks into two pieces, two parts. In this case, there are two phases. One is a confined phase and one is a Coulomb phase. And these two phases are separated by the first order phase transition, which happens at a critical value of the coupling. Now the coupling I will call beta. I will explain why beta. And it's a critical value of this coupling. And this can be measured. And it can also be calculated. First of all, it can be measured by a lattice simulation. So I will discuss these systems partly because the existence of this phase transition can be proven beyond any doubt by putting the system on the lattice and computing in the standard way the expectation value of a gauge invariant operator and look at the discontinuity that it may have, and that fixes the position of the phase transition and the value of the critical coupling. And that can be done for SU2, let's say, in 5 dimensions, and 6 dimensions, 7 dimensions, and 8 dimensions. And then after that becomes very, very difficult to measure things on the lattice. It becomes practically impossible. But up to 8 dimensions, it has been computed, and it has been computed, the numerical value is known. Now, on the other hand, one can also compute the critical value of the coupling by analytical methods. So one can regulate the system on the lattice again and compute it analytically via mean field expansion. So notice here that this phase transition occurs in the interior of the phase diagram, and it typically occurs at a value which is of order 1, as long as the dimensionality of the system is low, is relatively low. Now, it happens so that one can derive an exact formula for the critical value of the coupling, and basically it's a number, which I don't write here, it's something like 6.7 or something, over d minus 1. So in particular, this means that as d is taken to infinity, the confined phase shrinks and finally disappears completely at infinite dimensions. This just means that one cannot form flux tubes in infinite dimension. Now, another very important aspect here, which is not so obvious, is since we are trying to relate a system that can be really regularized, put on a lattice, and computed, and related to continuum quantum field theory, there has to be some kind of a link. That's a complicated issue in general, but perhaps the most important relation is a simple relation to write, which relates the scale, the regulating scale of dimensional regularization, nu, with the lattice spacing, A, and just because of dimensional analysis, of course, mu has to be inverse 1 over A times some dimensionless function. And now this dimensionless function is an extremely complicated quantity to compute. It has been computed for very, very few theories and perhaps only for QCD in high energy systems. Nevertheless, this is the relation, and one can, instead of computing it, one can fix it numerically somehow and use it. But once, the important thing is that once one has such a relation, one can relate non-perturbative results from the lattice to continuum quantum field theory. Okay? Now, another aspect is that since we are ultimately interested in four-dimensional physics, and we have these phase transitions in 5 dimensions or higher, we have to somehow reduce to 4 dimensions. So there are 2 ways to reduce dimensionality. One is compactification. We're all familiar what compactification is. And the other one, which is not as easy to handle, is localization. Localization is when the system, if it's 5-dimensional, let's say, breaks into an array of 4-dimensional slices. Okay, so this is a non-perturbative effect. Compactification, on the other hand, can be treated perturbatively. That's why we are so familiar with it. Localization is a non-perturbative effect. It occurs in special circumstances. It appears localized. Hyperplanes appear as solitonic solutions. In string theory, they appear as D-branes, etc. So because of that, because I will be discussing both of these regimes, because these are just 2 regimes of the phase diagram of the system, I will refer to the localization situation as branes sitting along a 5th dimension, let's say. And then finally, an even more obscure property is that phase transitions, these quantum phase transitions, seem to have shadows. So what does that mean? See, in 5 dimensions, as I showed you here in this picture, in 5 dimensions, there is a sharp first order phase transition that separates the confinement from the Coulomb phase. Now, if I take this 5-dimensional SUN system and compactify one of its dimensions, and start shrinking the compact dimensions towards 0, what will happen is that the system at some point, if I take the radius of the circle small enough, it will start behaving as a 4-dimensional system plus corrections that become smaller and smaller as I shrink the circle to 0. And finally, when I shrink the circle really to 0, it will become a 4-dimensional system. What happens to the phase transition? Well, it disappears because 4-dimensional SUN does not have a phase transition. It has only one phase. It has only a confined phase. However, it leaves behind a shadow, and the shadow is that there are still 2 regimes in the phase within this confined phase, where the system behaves completely differently, and these 2 regimes are, roughly speaking, separated by a scale, which is lambda QCD. So that's the shadow of the 5-dimensional phase or higher dimensional phase transition, as a 4-dimensional observer sees it. Okay. Now, let me go to now a specific construction to illustrate some other interesting properties. So let me take now a 5-dimensional lattice SU2 Young-Mills. And as you see, there is this blue lattice cubes. This is the bulk. But and then for reasons that I will explain later, I will add also, I will impose some boundary conditions on the SU2 gauge field so that the 5th dimension becomes an interval with 2 branes sitting at the 2 ends of the interval. And on these 2 branes, the symmetry reduces and the spectrum is just a U1 gauge boson and the complex scalar. Okay, many of the properties that I will describe do not depend on the existence of these boundaries. So you can just take the bulk, the blue links, the blue lattice to refer to. Certain interesting properties also involve the boundary, and I would like to also to talk about those a little bit. So now this is the phase diagram of the system. This phase diagram is defined by 2 couplings. As you can see here, there is a coupling beta 4, which is the coupling along the 4 dimensions. And then there is a coupling beta 5, which is along the 5th dimension. And I can also parameterize the phase diagram in an equivalent way by, instead of beta 4 and beta 5, by beta and gamma. Beta 4 is beta over gamma, beta 5 is beta times gamma. In this case, beta is called just the coupling and gamma is called the anisotropy parameter. This is very useful to keep in mind. And the important information which is hidden in this definition is that this anisotropy parameter governs 2 things at the same time. It governs the size of the extra dimension, of the 5th dimension, and the coupling on the 4-dimensional branes. Okay. This is not so usual. You can do this very easily in a continuum regularization. On the lattice is very natural to do. It is possible to do it in a continuum, as we will see, but it is very natural to do it on the lattice first. Now, this is the phase diagram in terms of beta 4 and beta 5. I will be, all these, this red line and this blue line are first order quantum phase transitions. One can think of I will be interested only in the blue line in this talk. And below the blue line, one can think of it as a confined phase. And above the blue line is a deconfined phase, which is a Coulomb phase without special boundary conditions, and the Higgs phase with the special boundary conditions. In which case, let me just make a comment, which to me is very interesting. I will not say much on this, but to me it's very interesting. Since now on the boundary there is an abelian Higgs system, basically, there is a Higgs scalar and there is a vector boson. And then this becomes massive since we are in a Higgs phase. The ratio of these 2 masses can be computed. Now we know this I will call this the rho parameter. We know the rho parameter because in the real world, in the standard model, we know the value. The value is 1.38 to 1.39, something like that. Now, if you take this very, very simplistic system and you put it on the lattice and you compute the value of this rho parameter, you find a very interesting surprise, namely that when you are away from the phase transition, this rho parameter is always less than 1. Then when you get closer and closer, the rho starts increasing. It becomes 1 in this light green area and becomes larger than 1 in this dark green area. And when you hit the phase transition, it takes the value 1.4. Okay, so this may be just a stupid numerical coincidence, but it's something very interesting. Now, let me now turn to some generic feature of this blue line, this blue line phase transition. So this blue line is there even with or without the boundary condition. And there is a very interesting fact that I would like to explain on this diagram. So here is a zoom of this blue line, and this dashed here line is the phase transition. Okay. Now I have called the Higgs phase above and this confined phase. I call it the hybrid phase, but let's call it confined phase. It's the same base, basically the same thing. And I have plotted two renormalization group flow lines that start somewhere in the interior of, let's say, the Higgs phase and approaches the first order phase transition. Now, there is these dots here. These dots are actual calculations. So these are actual calculations, QFT calculation. You compute the beta functions, etc. I don't show any of this. But what is important is that each of these dots, as I showed you in the example of the phi cube theory, phi to the fourth theory in 3 dimensions, each dot is characterized by a value of the regulating scale mu of dimensional regularization. And the color code is such that as we go from red towards blue, we go from the infrared to the ultraviolet. So you see here you have this, red, and then becomes orange, and then it becomes yellow. And on the phase transition, it takes a finite value because it's a first order transition, not a second order transition. It's not a fixed point. And it has some value and it corresponds to a blue dot. Now, there's already something very interesting here is the fact that the line ends at an ultraviolet point. So this is indeed consistent with this example that I gave you of the Wilson-Fisher point, which is not exactly a fixed point. It is trying to become a fixed point. So the cutoff goes to higher and higher values as you approach the phase transition, and it stops at a finite value on the phase transition. But now there is another very interesting fact here, is that if you go to the other phase, to the confined phase, you can actually do the same thing, and this is non-trivial. Why? Because you see that on the other side of the phase transition, there is again another RG flow line, which is also characterized by some values of the scale mu. And again, we have a red, an orange, a yellow, a green, and a blue. There's also a green here that you can't see because the tip of the arrow covers it. But we have the same colors. This means that if there are these two RG flow lines, they have to span the same values of the regulating scale because they belong to the same lattice. So this means, in particular, for example, that this red point corresponds to the value of a cutoff, which is the same as this, is the same with the value that corresponds to this red point. And the orange point has the same mu with this orange point, and the yellow, the same with the yellow, etc., etc. And then they end up landing on the same point on the phase transition. This means this is highly non-trivial because this means that these two RG flow lines are correlated. In what way? Well, one can be quite explicit about it. One can compute a physical quantity in one of the phases, which is a function of mu. One can compute another physical quantity in the other phase, which is another function, different function of the same mu, and then one can invert these two functions for mu, and this mu is the same. So this means that since the left-hand sides are equal, then the right-hand sides are also equal, and then this means that the physics in one phase determines the physics in the other phase, which is sort of a duality. It's a very raw form of duality, but it is a duality. Now, another very interesting property is that since on one side, since the RG flow in the confined phase, it is an RG flow of a confined phase, we know its boundary conditions. We know the string tension, we know the value of lambda QCD, if you wish, for an SU2 theory in 4 dimensions. And that determines the cutoff on the phase transition, which in terms is the cutoff of the theory in the Higgs phase. So if this cutoff is forced to be low by the confined phase, then the Higgs phase will have an effective field theory description with a low cutoff, which is also something that you can't generate easily in quantum field theory. Ora, so now another thing that I alluded to before is the fact that this system, since it's generated by the lattice, it has no polynomial interactions. It has only derivative interactions. And that's, here it is, I show it explicitly. It has a kinetic term, and the first non-trivial term is phi squared box phi squared with a cutoff mu star. Mu star is the value of mu at the blue point on the phase transition. That's the cutoff of the theory. And it's not an irrelevant operator. It's the most relevant operator. Of course, you can add higher and higher derivative terms, and this just has to do with the fact that you can have more RG flow lines, more RG flow lines, RG flow lines. And now notice another very interesting property is that if you start plotting RG flow lines, they will end up with a value of the cutoff, and a UV value of the cutoff, which will be different for different points along the phase transition. And here is the color code again. There is a yellow, there is a green, there is a blue, and there is a deep blue here. So as you slide along the phase transition, you go from the infrared towards the ultraviolet. And that would not be possible, for example, if this line was a fixed line, if it was a second order phase transition. There would be no RG flow along the line. So can we interpret the phase transition line itself as an RG flow? Now, in the infrared limit, the yellow point here on the phase diagram is the infrared, and it's a regime where the fifth dimension, as I told you, the phase transition is parameterized by the anisotropy gamma, and the value of the anisotropy gamma at the yellow point in the infrared tends to infinity. And that's a regime where the fifth dimension becomes smaller and smaller. And for gamma approaching infinity, the fifth dimension disappears, and you have an SU(n) Yang-Mills theory on the brane, which is at weak coupling in the asymptotically free regime. That's just a fact. That's the way the lattice is set up. Instead, in the UV regime, in the other limit, when the anisotropy goes to 0, it is exactly the opposite that occurs. That what happens is that the dimension transverse to the brane becomes infinite, and the coupling along the brane, did I say it upside down? No, sorry. Here I said it upside down. The circle shrinks to 0, and the coupling along the brane becomes strong, becomes infinite. So you have a strongly coupled Yang-Mills on the brane. In the other limit, when gamma goes to 0, the extra dimension becomes infinite, and the coupling along the brane becomes 0. Also, the coupling along the extra dimension goes in the opposite direction as the coupling of the brane. So it means that when the coupling along the brane goes to zero, when this is a weakly coupled theory, then the coupling along the extra dimension is strongly coupled. So what does that mean? It means that if you think about the strong coupling, the effect of the strong coupling forming flux tubes along the extra dimension, these flux tubes becomes more and more stiff. And not only that, but also we know that as a flux tube becomes elongated, it becomes broader and broader. So in the limit where the anisotropy goes to zero, the extra dimension, the flux tubes along the extra dimension become infinitely long and infinitely wide and infinitely strongly coupled. What is it? What is there left? There is an SUN Young-Mills again, four-dimensional, at weak coupling. So in the two limits of the phase diagram, the yellow point and the blue point are the same theory, SUN Young-Mills, except that in the infrared, it is strongly coupled, and in the ultraviolet, it is weakly coupled. So these are connected, these 2 points, if you wish, they can be connected via an inversion of the coupling, for example. Of course, that's not an RG flow, but it's good to know that you start from the same theory and you end up with the same. Anywhere in between, the theory is something much more complicated because there is a fifth dimension which is not zero, not infinite, somewhere in between, and basically it's a if you wish, in the brane language, it's a four brane with one of the circles compactified. So how do you describe then an RG flow from the infrared to the ultraviolet? Well, I don't know the answer, but this system resembles very much for example, in the Witten-Sagai-Sugimoto solution, where you have a D4 brane, you compactify one of the directions along the brane, you impose some boundary conditions so that you get rid of the matter, and that should correspond somewhere where this green point sits. So then how do you possibly describe an RG flow? Well, in this case, you have to introduce an anisotropy. And there are such solutions, D4, D6 solutions with an anisotropy, except that here the anisotropy is along the fifth dimension. Usually these solutions, they have an anisotropy along the brane, the four of the dimensions, not the fifth dimension. And also another even more, I think, important difference is that the anisotropy in the D4, D6 solutions are introduced by a CP odd operator, and here everything is CP even. That doesn't mean, of course, that CP cannot be broken spontaneously, or the RG flow as seen from the string theory side is just possible by introducing a CP odd operator. And that's just saying that if you would try to implement non-perturbatively an RG flow along the phase transitions, you would have a spontaneous breaking of the CP symmetry. That would be a very interesting solution that, as far as I know, is still doesn't exist. Now, let me just say one more last thing. Let me just plot the same thing in a very cute way. So now here the axes are the minus inverses of the dimensionful couplings, whatever those are. If there is a UV phase transition, then this phase diagram must have a throat. And it is more pronounced if the phase transition is second order, if there is a continuum limit, because then the throat is infinite. Okay? If a phase transition instead is first order, there is a throat, but the throat is not infinite, has a finite size. And the difference is very easy to see in this case, is when the throat is infinite, there is no obvious way to go if you start from an RG flow, like say here, and you fall into the throat. There is no obvious way how to get out from the throat, first of all, and which RG flow to ride as you exit the throat. Okay, that's just saying it in a different word for that if you want to deform a CFT and you deform it with a mass, it's a parametric deformation. It's not an RG flow. Instead, when the phase transition is first order, the throat has finite depth, which means that you can ride an RG flow, go down the throat, and exit in a controlled way, some other phase, for example. 5 minutes, yes. Thank you. You can exit on the other side and then ride the RG flow on the other phase, in the other phase. In what way? In the way that I showed you, because then the RG flows are correlated. And then finally, it's a fact that I would like to stress here, which is not it's not easy to see in perturbation theory. And the fact is that such a phase diagram breaks basically in three parts. Okay, there is one part which is the Gaussian, the vicinity of the Gaussian fixed point, which is the regime with which we are very familiar. This is perturbation theory, etc., etc. And then there is a classical limit. Okay, everything goes as usual. There are marginal, relevant, irrelevant operators. The irrelevant are irrelevant in the continuum limit. The continuum limit can be thought of as a classical limit, etc., etc. Then, if you enter in the interior of the phase diagram, usually you lose the sense of direction. How do you know that? Well, first of all, the usual thing that we say is that perturbation theory breaks down. That's a statement that we make, but we don't exactly know where does it, why and where, etc., etc. On the lattice is easier to see, because if you are in this regime, anything that you compute is dominated by the cutoff. And that's a very strong signal that there are no sensible, there is no sensible effective field theory that you can write down, and that therefore there is no sense of direction which is given by the direction of towards in which the RG flows evolve. Okay, so this is a regime where there is no sense of direction. You can express it in many different ways. No effective field theory, no direction in obvious direction of the RG flow lines, etc. And then there is this blue regime that we basically concentrated on this in this talk, where you approach the phase transition. There is no other way. There's nothing else you can do. So you have to fall in the throat, because that's where the energy scale is pointing towards. It's pointing towards the ultraviolet in this case. Okay. So once you are there, you fall into the throat, and then you can exit on the other side in some other phase, in the confined phase, but then the confined phase, let's say, if it's a confined phase, determines via this generalized sense of this row duality that I explained, the physics on this side of the phase transition. And all these things are as generic as the appearance, the existence of these quantum phase transitions are. And as far as I can tell, well, Young-Mills theory is in dimensions D higher than 5 or higher. They're necessarily there. Also, these phase transitions, since they have shadows, they leave their imprint on four-dimensional their four-dimensional counterparts. Well, in this talk, I assumed, I didn't say it explicitly, but I will say it now, the dimensionality of a system is just a coupling. Okay, so you can take it to 0 to infinity just like any other coupling. So five-dimensional systems which possess these phase transitions, they leave a shadow in lower dimensional systems like the four-dimensional system by taking a coupling, which is the dimensionality, to 0 or to infinity. So in that sense, if our universe at any point in time have sat near such a first order phase transition, all this should be relevant. Okay, so I don't know whether, of course, I don't know whether this actually happened, but if it happened, then all this should be relevant. Okay, so we demonstrated some properties of RG flows near first order quantum phase transition. And of course, I don't know how generic or physical these features are, but certainly they are interesting, and also they can have they can motivate also experts to look for solutions, as I said, which are solutions in the D46 system and so forth. Thank you. So since I am the moderator, I will ask if you have any questions, and if you don't, then we can move to the last speaker of the session. Okay, thank you. Then if the last speaker is here, Nobuyoshi Ohta, I believe. Please correct me if I'm wrong. Nobuyoshi Ohta should be the last speaker according to the program.